output and an input variable. At other times, you're dealing with two input variables to check for correlation. It's not always a relationship between an input and output or two inputs. It can swing either way. So now if it moves to the right, meaning that if X decreases, Y decreases. If X increases, Y increases. If they both moved in the same direction at the same time, then it means that these two variables are positively correlated. Again, now since it's a measure of the degree, it gives you to what degree is this relationship. Otherwise, it wouldn't be a measure. Most of the times when you just observe, you can tell whether they are moving in the same direction or in opposite directions. But when you compute this measure, it will give you the exact degree to which they are related. So at times you compute a measure, we normally say if it is around 0, if it is approximately equal to 0, we normally say that they are more or less independent, or the degree of relatedness is small. If they are around 50%, if you get a value, say 0.5 on either side, negative 0.5 or positive 0.5, then you say that they are moderately related or moderate association. That is, if there is at least a 50% chance that they'll increase in the same direction or move in different directions, then you talk of a moderate association. If it goes above, in statistics, we prefer that it goes above 90 for us to talk of a high correlation. But if it is above 80, you now say that there's a strong relationship or a strong association between the two variables. So this correlation, coefficient of correlation, only gives you that degree. If you want to find the exact value for which you can now say, if I got a correlation coefficient of, say, 0.9, a correlation coefficient of 0.9 indicates that there is a 90% association between our variables. 90% is pretty high. So you say there is a high association or a high degree of relationship between our variables if you are dealing, say, with X and Y. But now if I want to say to exact precisely what amount of Y is explained by X, that is where now we compute the coefficient of determination, or the rho squared or R squared as you know it. That R squared will now tell you, because if I take rho squared here at 0.9, I have 0.81. That 0.81 now tells me there's an 81% of the outcome in Y is explained by X, meaning the remaining 19% can be explained by other factors, but the X factor holds 81%. So this coefficient of correlation is used to also define independence, such that if you find that the correlation coefficient is 0, then you talk of X and Y being independent or having no relationship. So this aspect of the correlation is not new. It is something that you've covered before. We are just going to look at it from the perspective of now two jointly distributed variables. That is, given our function fxy, how are we going to obtain the correlation? Now, before we obtain the correlation, there's this concept I want to introduce now. What might be a bit foreign is the covariance concept. The covariance, you know, we normally deal with variance. Variance is not new to you. Covariance, meaning you're taking the variance between 2 or 3 or more variables. So when I take the variance, say I have X and Y, I have my variables X and Y. If I take the variance of X, since they are jointly distributed, I can get the variance of X. We already saw that this is possible since I can get the marginal distribution of X from the joint distribution of X and Y. So I can get the marginal. So I can get the variance of X from its marginal. I can also get the variance of Y from the marginal or the joint. Doesn't matter how you approach it. You can get the variance of X and you can get the variance of Y. Now, if I want the variance of the combined variable XY, now this is no longer just a variance, but what we call a covariance. A covariance meaning it is a variance of two or more variables. Fidelis, you'll just have to bear with me. Just let me know if it persists. I warned you early enough. I've been trying to fix it since morning and I don't know. If it persists or gets really bad, just let me know. I'll have to restart the session again. So I have a covariance of xy the covariance of xy is now what we are going to define. This joint variance is what we are calling a covariance. So if I am dealing with a random variable, say x and y are my random variables, and they are jointly distributed with the PDF that we've been using, fxy, then the covariance is usually denoted as the expected value of x minus mu x minus mu x into y minus mu of y. And here, mu of x is the mean of x, the expected value of x. Mu of y is the expected value of y. This is as a result that when we are defining the variance of x, we normally say that we take the expected value of x minus mu squared. Now this square in our x minus mu, is normally squared. It's usually the second central moment from the mean, Now this square in it, since we are dealing with two variables, if you take x minus mu x times y minus mu y, it's as if you've squared it, but not in the express terms of squaring. So it's as if we've squared it, but since we are dealing with two variables, you're considering the first variable times the second variable. It's still the second moment because we are still dealing with the two variables. So this expected value of x minus mu x into y minus mu y, this is what we call the covariance of x, y. And of course now it's going to be obtained using the definitions that we defined for obtaining expectations. If you're dealing with a discrete random variable, this will be the sum of x minus mu x, y minus mu y into fxy. If you're dealing with a continuous random variable, you expect that this will be the integral of the same value. So we have x minus mu x into y minus mu y. And then you have fxy dx dy. So that is what you're going to be dealing with when obtaining the covariance. But now we can simplify that function a bit by expanding, because we know that when you have this value here, the expected value of x minus mu x and y minus mu y, we can expand it a bit and see whether we can simplify that function. So the covariance behaves in the same manner as the correlation coefficient. What happens is that if the covariance is positive, then it means that both x and y are increasing in the same direction. That is, for large values of x, we have large values of y. For small values of x, we have small values of y. That is when the covariance gives a positive value. If the covariance is negative, on the other hand, then it means that for small values of y, we experience big values of x and vice versa. So it behaves in the same manner as the correlation coefficient. When you get a covariance of 0 this is something that you should note and note very carefully, and do not mix it up. A covariance of 0, unlike in the correlation coefficient where we have said if it is 0, then it means x and y are independent. If the covariance is 0, it does not necessarily mean that x and y are independent. But if x and y are independent, the covariance will always be 0. Kwa pamoja? Is that understood? A covariance of 0, if covariance of xy is 0, it does not necessarily mean independence. But if there is independence between x and y, if x and y are independent, then the covariance will definitely be 0. But if you compute the covariance and get 0, it does not mean they're independent. But you can check for the independence. If they're independent, then most definitely the covariance will be 0. But the covariance of 0 does not always imply independence. That is why we use the correlation coefficient to define independence, because this covariance measure is a bit sensitive to the scale of measurement that you use. Due to that sensitivity, it is not always a clear indication of independence. If it is 0, does not always mean there is independence. But if there is independence, it will certainly be 0. Note that and note it carefully. So I was saying it has the same interpretation as the correlation coefficient, meaning that if it is negative, they are negatively correlated, or they have negative covariance, they are moving in different directions. If it is positive, they are moving in the same direction. Whether they are increasing together or decreasing together, they are moving in the same direction. That is for positive correlation and positive covariance. So I was saying we can try and expand that definition and see whether we can simplify our function there. Is there any screen it is sharing? Because this thing today has really put me to the test severally. So I'm saying that the covariance of xy, we've said will be defined by the expected value of x minus mu x, where mu x is the expected value of x, and y minus mu y. This is from the definition of variance. But now, since we are taking the variance of our combined variable x and y, then we end up with this definition, where mu x is the expected value of x, and mu y is the expected value of y. Let's expand this, and you notice that the expectation can only affect variables. And you remember we said this expected value of x and the expected value of y, or rather the mean of x and y, those are constants, so they cannot be affected by the expected value. So we first start by expanding this function. If you expand it, you're going to get this is the expected value of, you're just opening up this bracket. So you're going to get xy minus x mu y minus y mu x, and then you have plus mu x mu y, just the ordinary expansion. So after expanding it, we can now supply that expected value, knowing that it will only affect the variables. It will not affect the constants. So we are supplying it inside the bracket. We are now putting this e inside the bracket. Of course, it's going to affect xy. So we are going to have expected value of xy minus mu y is a constant. So mu y will not be affected by the expected value, but x will be affected. So we are going to have mu y and then expected value of x. Same as here, again, mu x is a constant. so it won't be affected. And then we have expected value of y. And then finally, this last term, mu x, mu y, that is a constant, so it cannot be affected by the expected value. So now from there, we know that mu x is expected value of x and mu y is expected value of y. So we can rewrite it in that format. We have expected value of xy minus mu y. Now this, since expected value of x is mu x, we can just replace that with mu x minus mu x, mu y, and then plus mu x, mu y. You notice that these two terms here are going to cancel out because we have a product of mu x, mu y, minus that plus that, they cancel out. So you're left with the expected value of xy minus mu of y, mu of x. And by definition, we have said that this mu of y, mu of x, we have expected value of xy minus mu of y is expected value of y, mu of x is expected value of x. Doesn't matter in what format you'll put it, that it's still the same, it's just a product. So in short, the covariance of xy is usually given as expected value of xy minus expected value of x times expected value of y. So when you're asked to obtain the covariance of x and y, you'll never be told to obtain the covariance of x alone. The covariance is always a term that is for two or more variables. So when you're expected to get the covariance, actually two variables, that's when we talk of covariance, because they are sharing the variance. So we have this covariance for this level, we're only dealing with two variables. So anytime I ask you about covariance, I expect you to get first the expected value of the combined term xy, like we did, whereby if it's xy, we are taking the double integral xy, fxy, dx dy. If it is discrete, same thing. Again, expected value of x as we did in the last class, and the expected value of y. Then you'll just take the product of the expected value of x and y, less it from the expected value of the combined term x, y. That gives you the covariance. The covariance does not have defined limits like the correlation coefficient. So it could be any value from negative infinity to infinity. But we are saying that if it is negative covariance implies that the two variables are moving in different directions. And then if it is positive, it implies that the two variables are moving in the same direction. If it is zero, it does not always mean independence. So that is covariance. I would like to also define correlation so that we can look at the examples for covariance and correlation simultaneously without having to first look at the covariance, then go back to correlation. So for the correlation, I've told you due to the shortcoming, I've told you that covariance is normally has a weakness that the value is very sensitive to the unit of measurement that is used. Due to this shortcoming, then that weakness can be seen in that a covariance of 0 might not signify independence. So we normally have a better measure, a more refined measure that counters that shortcoming. And this is now what we have called the correlation coefficient. This correlation coefficient, or what you just call rho, is what we are going to define now as, we are going to call it rho of xy, because it's the correlation between variables xy. So if we have the random variables xy and we have the covariance, because we are going to need the covariance in the computation of the correlation coefficient. So assuming that x and y are random variables with, of course, joint distribution function fxy and covariance function cov xy, and we can get the standard deviation of x, let's call it sigma x, and the standard deviation of y, call it sigma y. These are standard deviations. So assuming you can obtain all this, we are obtaining sigma x and sigma y from the definition of the variance, where we said that if we want to get variance of x, we know that this sigma squared will be the expected value of x minus mu x squared, and the variance of y from probability and statistics 2, this is just from probes 2, it will be expected value of y minus mu y squared. So you will have to get these expected values, mu x and mu y, you will have to get them so that you can now subject them to this expected value. After you obtain that expected value, then you can now proceed to compute the correlation coefficient. Our rho xy is now given by covariance of xy all over the standard deviation of x times the standard deviation of y. So for this correlation coefficient, you need the covariance and you also need the variance of x and y so that you can obtain the standard deviation from that. Note that all these values, the covariance, the variance, the expected value of x, mu y, all those are constants. So you will not be dealing with any variable at any point when computing these measures. All these are constants. The covariance is a constant, the variance is a constant, the expected value is a constant. So the correlation coefficient is defined by that. And also you have to note that it lies between the value positive 1 and 1. As it approaches 1, it signifies strong correlation. As it approaches 0, the correlation or the association between the two variables decreases. And I told you, if you want to get the exact interpretation of what percentage of x is explained by y or vice versa, then you get the rho squared, which is usually a value now between 0 and 1, because if you square negative 1, that's 1. So it's usually a value between 0 and negative 1, and it is called the coefficient of determination. For those who are going to continue with statistics, there are those who have already picked statistics. The BMC group, there are those that are in this class. This coefficient of correlation is very important in statistics. Coefficient of determination, sorry. It's very important in statistics, and it is the one that gives you what exact value, what is the exact degree of association in that. If I get a raw value of 0.8, for instance, implying that rho squared is 0.64, means that there is a 64% of y is explained by x. What happens to the other 36%? 36% is now explained by other variables or by chance. We normally just say it's explained by chance. It's random. So these are squared every time you're inputting your data for analysis in the various softwares that you use. You're going to encounter the r squared, and that r squared, the interpretation is just from this coefficient of correlation. We obtain the coefficient of determination, which is called the r squared, and the interpretation is, as I have told you. The correlation coefficient just tells you the strength of the relationship. So that is the covariance and the correlation. So I want us to look at some 2 or 3 examples here. Examples, copy. I'm hoping we are together mpaka hapo. I'm hoping mmepata the concept of covariance and correlation. Is there anything showing on your screens? Last part on correlation, what about exactly? What was it about? Kuna example inaonekana hapo ya suppose x and y are discrete random variables. On my end imekataa kuoneshana. Just a blank screen. Suppose x and y are discrete random variables with joint PDF xy. There it is. I think it is now visible. This example here. Take that example down. I want us to compute the covariance and the correlation of x and y. I want us to compute the covariance and correlation. Although it's a question that we've been dealing with before, we've dealt with it through and through since we started this course. So it's a question you already have, but now I want us to compute the covariance and correlation for that particular question. Dixon, I'm still waiting for your exact question. Which exact part? Last part of correlation, where correlation is a value between -1 and 1 ama. So the formula of the correlation coefficient just requires you to have the covariance that we are going to compute. So we are going to see how we are going to compute the covariance right now. And then you divide this by the standard deviation of x times the standard deviation of y. Bearing in mind that the variance or the standard deviation is an expectation. So this is simply expected value of x minus mu x squared, and the expected value of y minus mu y squared. So that is what is going to give us the variance. So after you obtain the variance, the square root of the variance, since this will be a constant, expectations usually yield constants. So since it will be a constant, we are just going to take the square root of that constant, will be the variance of x, square root of this will be the variance of y. Apply it in this formula, and then this formula gives you the correlation coefficient. So there's quite a bit of computation when you're dealing with this covariance and correlation, because you have to obtain all those expected values. For the covariance, we have said you need the expected value of xy, you need the expected value of x, and you need the expected value of y. So you're going to compute quite a number of expectations before you get to your results for the covariance and correlation. But you just take covariance of xy over the standard deviation of x times the standard deviation of y. And again, it should be a value between -1 and 1. Is that clear now, Ndara? So I'm here. This is the output that we have. We are expected to compute the covariance. I've told you we are computing the covariance and the correlation. So we are going to start with the covariance because we need it in computing the correlation. So we are going to start with the covariance. If you have the question, I'm leaving this screen since we've repeated it over and over again. So I want to compute the covariance of xy, of which we have said this should be the expected value of xy minus expected value of x times expected value of y. I think when we were computing expectations, when we were looking at bivariate expectations, we computed the expected value of xy for this function. Able recall back from your notes, because I can see we computed the expected value of xy and we got 6 out of 28. Check from the last class when we were dealing with these expectations. Check, I can see we computed the expected value of xy. We obtained it as 6 out of 28. So what I want us to compute now is the expected value of x and expected value of y. Have you traced it from last week's class? Expected value of x, which is our mu x, this is just, this is a discrete. So this will be summation of x fxy, since it is discrete. So we are summing our x fxy, and this we said will be the same as summing x f1 x. That is x times the marginal of x, because if you sum over the values, if you sum fxy over the values of y, you'll end up with the marginal of x, and then now you can sum the x times the marginal of x to get the expected value of x. Can you give me that expected value, please? So that I can be sure that whatever we did in the last class was well understood. Give me that expected value. X ranges between 0 and 2. So I expect 0 times I expect that since the marginal of x is for when x is 0, x is 1, x is 2, and the values of x are between 0, 1, and 2. So can you give me the expected value of x? The expected value of x Kwa pamoja kweli ama I'm on my own? Are we together? Are you giving me results? Are you quiet because you're giving me results, Ama? Perfect, Edgar. Tumefikiana hapo. Aya, tuende the next one. The next one, expected value of y. Wengine wangekuwa wakicompute expected value of y. Very good, Grace. Give me the expected value of y. The expected value of y now, you're supposed to get the sum of y times fxy. So this should be equals to y. Will be the same as sum in y times the marginal of y. Great, Duncan. Sasa tufanye ya y. Can see we are very together. So yeah, y again, y is between 0 and 2. So we have this will be equals to 0 times f2 of 0 plus 1 f2 of 1 plus 2, because it's y fx f2y. So y0, y1, y2, f2 of 2. One over 2, are we all getting that? Thank you very much, Alex. 1 over 2. Is everyone able to obtain that? So we have 1 over 2 is the right answer. Thank you very much, James, Dominic. So for those who might not be following, this is where it's coming from. The marginals, remember, were already at the last row and the bottom column of that particular distribution function that we were given. So it's just a matter of summing them up and multiplying each by y, and you end up with 12 over 28 plus 2 over 28, which is 14 over 28, or a half, as has been reported. So now we have our covariance of xy. Since we already have the expected value of xy, and we have the expected value of x and the expected value of y, we're just going to take that 6 out of 28 minus, we had 21 out of 28 times a half. And that will be the covariance for that particular output. What do you get? It's 12 minus 21. 12 minus 21 is negative 9. So you notice that the covariance is negative. which simply implies that there is a negative, some sort of negative association. Perfect, Dominic. There's some sort of negative association between our variable x and y. There is an association, yes, it's present, as we can see from the value we are getting for the covariance, but it is negative, meaning as x increases, y decreases, and vice versa. They are moving in different directions. Let's obtain the correlation coefficient for the same. Since we already have the covariance, perfect, Emmanuel. Since we already have the covariance, what we have to do now is obtain the variance for x and y. So we have the expected value for x, expected value for y. We have obtained all that. So the variance we know, for the variance we need the expected values. So we are going to use our correlation coefficient, rho xy, should be equals to covariance of xy all over sigma x, sigma y. So now here I'm saying we already have this covariance, so we just need to compute sigma x. We'll need the variance, and we know to compute sigma x, we are going to take the expected value of x squared minus expected value of x squared. That is what we define the variance as. So we already have this. I'm saying we also have the expected value of x. So we only need the expected value of x squared. And from our table, that will be expressly obtained, because this will be the summation of x squared fxy. That will be the summation of x squared fxy. So this simply means we are dealing with the sum Let me just deal with it step by step, because I haven't checked whether I'll get the same result, but you should get the same result. So I have my x again is from 0 to, let me check whether first of all it will give me the same result instead of writing this whole equation here. I don't want to have to deal with that whole equation. So I just have the sum of x squared f1x. So x squared, I have 0 squared times f1 of 0 plus 1 squared times f plus 2 squared times f1 of 2. So this will be 0 plus 15 over 28 plus 2 squared, that is 4, times 3 over 28. So this is 15 over 28 plus 12 over 28, which is equals to 27 over 28, meaning that the variance of x will be equals now to, since we have the expected value of x squared, this is the expected value of x squared, and we had the expected value of x from the computation of the covariance. We'd obtained it as 21 over 28. So the variance will simply be 27 over 28 minus 21 over 28 squared. So what do you get there? What do you get? You're going to have to check this. I noticed that I hadn't yet confirmed these values. I think you get 315 over 784. Can someone check that that is the answer we get? Yes, or 45 over 112 if you simplify it. I've confirmed it is okay. And then now we have the same. Give me expected value of, we have for the variance of y. Variance of y, we need expected value. Yes, 45 over 112 for that. Simplifies to that. Of y squared minus expected value of y, all that squared. So I need the expected value of y squared because that is what we do not have. Give me the expected value of y squared really fast. We're going to have this should be the sum of y times fxy so this should be sum of all y squared f2y. Again, y was from 0 to 2, so we have 0 squared times the marginal distribution for y at 0 is 15 over . We had 15 over 28. Perfect. Yes, 16 over 28 is the answer. Good. Then we have 1 over 12 over 28. And we have 4 times 1, that is 4 over 28. So we have 12 over 28 plus 4 over 28. That is what we are yielding as 16 over 28. Then now from there, we can obtain now the variance of y, which will be y squared we had obtained from the previous question expected value of y, you told me was a half. So now this variance of y will simply be 16 over 28 minus a half squared. And what do you get? Confirm that is what you get, 9 over 28. So now we proceed to obtain the square root. We are just going to obtain the square root while obtaining the correlation coefficient. Now to obtain rho of xy, we say this is covariance of xy all over sigma x, sigma y. Or if you have it squared, you just get the square root. So we are going to get covariance of xy was -9 over 56. We've obtained sigma x. Sigma x is, what did we say it was? 45 over 112 times 9 over 28. And you get the square root because we want the standard deviation, not the variance. So if you deal with the variance, always remember to get the square root. So give me that value. I don't know if you're all getting that. Negative 0.4472. Interpretation. What is the interpretation of that? How do we interpret that? How do I interpret that? How do we interpret that? Alas, nimewambia tu saizi interpretation. When you're reporting on the correlation, you just talk about the degree of associatedness. So we are going to have this is negative. So they are negatively correlated. So you first note that negatively. Rather, you say your variables x, y, x and y are negatively. Actually, instead of saying they are negatively and then we say the correlation is moderate, we can just say they are moderately negatively correlated. Or you just talk over moderate negative correlation. Moderate negative correlation. I told you in statistics, you always have to interpret your numbers. Otherwise, they are just values with no meaning. The moment you just say there was moderate negative correlation, already you know it's around the area of 0.5. It's not strong, it's not weak. It's just average between x and y. Negative meaning as x increases, y decreases, which was seen from the covariance as well. The only thing is that the covariance did not give us the degree of that relationship. It just gave us an idea of the nature of the relationship, not the exact relationship. So we have, that is how we deal with correlation and covariance when dealing with a discrete. I'd like us to look at a case, unless there's a question on that. I want us to look at an example with a continuous before we jump to the next area of variance of random variables. So I want us to look at a continuous, unless there are any questions on that. Any questions? This is a question again we had last week. Just want us to deal with the questions that we already have. If it is positive, somebody wants to answer Juma. What does it imply if the value after computing is positive? Sasa Emmanuel, tumesema the correlation coefficient is always a value between -1 and 1. It can never exceed those limits. Because unless you're telling me that there is a relationship greater than 100%, of which that doesn't make sense, because 100% is as far as we go. So the correlation coefficient will never exceed 1 on the positive and on the negative. That's why we said strictly the correlation coefficient is a value between -1 and 1, and that is how you check whether you have the right computation. If you get a value that is less than -1 or greater than 1, then you're wrong. It can't be. Somebody answer Juma. What if it was positive after computing? What will the interpretation read like? We are waiting for James Nyamai. He seems to be typing something, hoping it's the answer. Variables are moderately, there is a moderate positive association between the two. So when you're dealing with this correlation coefficient, we normally say, let me just share something here for you to capture. Hoping I'll trace it, because it's usually someplace I don't know where. I know I gave you this when we were dealing with have you taken down this question? I want us to compute the covariance of xy. I want us to compute covariance of xy, hence, or just correlation. Just put it as the correlation. I want us to compute. By computing the correlation, it implies that you have to compute the covariance. It's just that when we're breaking down the question, you might pata umeambiwa part 1, what is the expected value of x, what is the expected value of y, expected value of xy, covariance of xy. In an exam scenario, you would expect it to be broken down in that format. This is just leading you to obtaining the correlation coefficient. So if you're asked to compute the correlation coefficient, what it means is that they expect you to compute all this, including the variance of x, including the variance of x and the variance of y. That is what is expected to answer that question. So we need to compute all those expectations so that we can come up with a correlation coefficient. As you ponder on that question, you can capture this for a second. this. This is the interpretation that we normally go by when we are explaining or interpreting the degree of correlation. So if it is positive or negative, one, that is perfect correlation, that is at 100%, either 100% negative or positive correlation, so we call it perfect correlation. If it is 90% negative or positive, is a high degree. 75 to 90 is sufficiently high, not high but not moderate, in between high and moderate. At 60 to 75 we have moderate. And this is zingine wamepeana hapo plus minus 60, 30, hizo ndizo moderate. Hapo between 30 and 60 or 30 and 50, that is where we talk of moderate correlation mostly. And then finally, if it is less than 30, there is a weak correlation, and at 0, we have no correlation at all. So those are the various levels and terminologies I expect you to use when you're dealing. So between 30 and 60, we'll be talking of moderate, positive, and either positive or negatively moderately correlated. And then we are going to talk of above, below 30, that will be weak correlation. Above 60 to around 90, there is sufficiently high. Above 90, it's high enough, and at 1, we have perfect correlation. I'm hoping that has now shed some light on the terminologies you're expected to use when you're dealing with the various concepts, the various interpretations for your correlation coefficient. So you always give it an interpretation. I wanted us to deal with that question. I want us to get the correlation coefficient for that question. So we are going to start by obtaining, what had we obtained last week for that question? We had obtained the expected value of xy. What was the expected value of xy? The one we obtained, the expected value of xy and the expected value of 3x plus 5y. I can see the expected value of xy was 1 over 3. Did we obtain anything else? We had the expected value of x was 7 over 12. The expected value of y was also 7 over 12. Is there anything else we obtained for that? We had the expected value of x times y was 1 over, oh, we already have that. We had the expected value of x times expected value of y, which we obtained as 49 over 1, 44. So with that, we were checking for independence. If you recall from that question, we were checking for independence. That's how we ended up obtaining all this. So now we just have to input these values. We have to input these values to obtain the covariance. So the covariance, our covariance where did that 4 over 12 come from? 1 over 3. Which will be equals to the expected value of xy minus expected value of x times expected value of y. This should be equals to our 1 over 3 minus expected value minus 49 over 144. And this was this will be negative. You can check, you'll get negative 1 over 144. You get negative 1 over 144 for the covariance. So now we have an idea that the two variables x and y are negatively correlated. So now to get the correlation, we just need to obtain the standard deviation of x and y. So we need the variance of x, which will be the expected value of x squared So we have the expected value of x. What we don't have is the expected value square. And since this is a continuous random variable, we will have to integrate that over y. The interval for y was 0, 1, 0, 1, and we have x squared into x plus y dy dx. Give me that. Give me expected value of x squared. Give me the expected value of x squared. So we have the expected value of x squared as shown there. So now we need to get the variance of x. The variance of x will be this expected value of x squared 5 over 12. And remember, we obtained the expected value of x as 7 over 12. So minus 7 over 12 squared. Once you obtain that, you're going to get 11 over 144. I'm hoping we are still together. Give me the variance of y. Can you give me the variance of y? Ndio nijue tuko pamoja. I'm waiting for that variance of y. First, give me expected value of y, then we proceed to compute the variance. The expected value of y, I believe that is the expected value of y. Sharon, that's the expected value of y. Expected value of y squared. Perfect. If you have any question as to how to obtain it, ama uko na shida na kuobtain, you speak now. We do it together. Or I assume that since people are getting it, then that is the expected value of y squared. So what is the variance? (11 over 144). Perfect. We have 11 over 144. So now we can proceed to obtain the correlation coefficient. The correlation coefficient will be covariance, which we obtained as -1 over 144. And we are dividing this by the square roots of variance of x is 11 over 144. Variance of y, you've also obtained it as 11 over 144. So this is -1 over 144 divided by 11 over 144. This is -1 over 11. Interpretation, -1 over 11 How do you interpret that? That is 0.09. 0.099%. That is almost no correlation, but anyway, it's very weak. We have very weak negative correlation between our x and y. There's a very weak negative correlation between our X and Y. Very weak because it is even less than 10%. .08, that is 8%. The R squared is at 8%. That is quite weak, very weak negative correlation between X and Y. Any questions on that before I move on to the next area? Any questions on that? That is the working that we've just gone through. Any questions? I'd like to move to the variance of the sum of random variables. Na leo hii bado lazima, but the other bit on conditional expectation and variance is quite direct. It wouldn't take us 30 minutes. Any questions on that? I proceed. If there are no questions, then I'll proceed to the next bit that I want us to look at. The equations here are a bit long, so I don't know if I'll have the strength or the stamina required to replicate them, or you might just need to follow them up. So I'd like us to look at the variance of the sum of a random variable. This is similar to what we were looking at when we were looking at the expected . Oh no, I've been talking to myself all that time. So as I was saying, when we were obtaining the expected value of a function of X and Y, we said that all we have to do is just supply this expected value inside these brackets, and it will only affect the variables. So we concluded that if you're asked to obtain the expected value of AX plus or minus BY, it's the same as taking A, expected value of X, plus or minus B, expected value of Y. So all you have to compute is the expected value of X and Y, and you are going to get the expected value of any other function of X and Y. So now the variance, according to the properties of the expectation, we had already said that the expected value will affect a variable, and the expected value of a constant is that constant. That is why the expected value of A remains as A, the expected value of B remains as B. So the expected value of a constant is a constant. I do not expect a value such as 2 to be anything else besides 2. So the expected value of 2 is 2. But when you talk about the variance, in the properties of the variance, back in probability and statistics 1, that's where we looked at the properties of the variance. In the properties of the variance, we say that the variance of a constant is 0. Why? Because you do not expect a variance, a constant to vary. That is, I do not expect the variance of 2. 2 cannot be within an interval. 2 is 2. So the variance of 2 from 2 is 0. It will just remain as 2. So the variance, since the variance is a squared difference from some point, there is no variance for a constant. A constant has 0 variance because it's constant. But when you look at a constant tied to a variable, we said that if I have the variance back in probability and statistics, 1, I have the variance of ax. The variance in this case is going to affect this variable because the variance is a squared deviation. It's going to square this constant, then multiply it by the variance of x. So we say this will be a squared variance of x back in probes 1. So now here we have 2 variables, x and y. So yes, we are going to have an a squared variance of x and a b squared variance of y. But now also remember, there is the term for the relationship between x and y. Since x and y are jointly distributed, then there is of course a covariance term. The covariance term for x and y will now be affected by these 2 values, a and b, because it is a covariance between x and y. So unlike the univariate case where we just said variance of ax is a squared variance of x, here we are going to have our a squared variance of x, sawa, and we are going to have our b squared variance of y. But now here in the middle is where we are going to have a plus or minus, now 2 times ab covariance of x and y. And that is how we deal with obtaining the variance of other variables. So allow me to explain it. Ikiwa tu venye iko hapo. So you move with me step by step. I don't want to replicate these equations. They might be too long. So we have here, if x and y are random variables having a joint PDF, we have fxy. Then the variance of a function of xy. So we are assuming any function of xy, that is ax plus by. You can have it plus or minus. We're only going to notice that the difference will be in this middle term. If it is plus, we are going to have plus 2ab. If it is minus, we are going to have minus 2ab. So we are going to have that to get the variance now of ax plus by. We know that the variance is defined as the variance of any term, say the variance of x is the expected value of x minus x bar squared. So it's the same thing here. Since we are dealing with the variance of a function ax plus by, this will be the same as taking the expected value of ax plus by minus x bar is an expected value. So we have an expected value within this expected value squared. All this is now squared. So we are taking that. This is what we have here. The variance of ax plus by will be expected value of ax plus by minus expected value of ax plus by, all that squared. Then from there, we are just spreading this expected value here, this expected value of ax plus by. We spread the expected value inside this bracket. So you're going to have a expected value of x plus b expected value of y, which will now yield this second part of the equation. Mpaka hapo tuko pamoja? Mpaka hapo tuko pamoja? Perfect. So sasa tu hakuna kitu bado tumefanya. Haya, tuanze sasa hapa. Now you can rewrite this function. This function here, ax plus by minus a expected value of x plus b expected value of y, that was in a bracket squared. If I remove that bracket, that means supplying this negative, this will be minus ax, this will be minus b expected value of y. So I end up with this function here. So I have the expected value of x plus by minus a expected value of x minus b expected value of y squared. Hapo tu I've spread this negative that was outside the bracket here. This negative, the variance, because the variance we have said is x minus x bar, or x expected value of x minus expected value of x, all this squared. So this negative that appears here is what is being supplied now inside that bracket. So we end up with that function. Haya, kutoka hapo sasa hapa tu tumefanya expand because it's a squared term. First of all, you put the like terms together. So we have the terms with a, the terms with b. Na tuka substitute for e of x ni mu of x na e of y ni mu of y. So sa hapa tutaweka ax na a mu x pamoja, tuweke by na a b mu y pamoja because they both have b. So when we do that, this is what we yield. So we now have ax minus a mu x plus by minus b mu y. I believe mpaka hapo tuko pamoja. The next step after that is factoring out what is common. Like in ax and a mu x, we have our a is common. So if you factor out a here, you'll have a into x minus mu x. And if you factor out b in this second part, b is common. In this first part, a is common. So if I factor out a, I'm going to have x minus mu x. If I factor out b, I'm going to have y minus mu y. Still we have it squared because we are getting the variance. Now if you write it in that format now, I have this function is what I come up with. So from there, I just need to expand it now. You know, if you're expanding, because these are just two terms, it's as if you're expanding x plus y. And you know, if you expand x plus y squared, you're going to get x squared plus 2 times xy plus y squared. Sindio? From the rules of expansion. So the first term is a x minus mu x. So that becomes a squared x minus mu x squared. And then 2 times x minus x plus y. So we have 2 times a x minus mu x y b y minus mu y. And then the last term is b into y minus mu y squared. So that will be b squared into y minus mu y. That is what we have here. Just expanding that term to handle the squared term. Bado tuko pamoja, I believe. So from there, if this was minus, if we had plus or minus, then this term here would have been minus. If this was minus, you know, this would have been minus 2ab x. This term is the only part that will change. Otherwise, minus times minus is positive. So the only negative would affect that point. So after that, we know if we supply the expected value, I'm now supplying the expected value, and we know that the expected value will only affect the variables. So in this case, a is a constant, so that is not affected by the expected value. So I'm going to have expected value of x minus mu x squared. I know this already is the variance of x. This by definition is the variance of x. Aya. Niko hapa AB 2ab x minus mu xy minus mu y. Expected value here will not affect these three terms because they are constants. So expected value of x minus mu xy minus mu y, we've just said that this is the covariance. That is the covariance of x and y. And finally, expected value of y minus mu y, this is the variance of y. So now, from there, just a matter of inputting. The variance of ax plus by will then be a squared variance of x plus 2ab covariance of xy plus or minus. Hapa ndio minus huingia, ndio kama uko na minus, that term will become negative, and then you have plus b squared variance of y. And that is the variance of ax plus by as we normally use it. So if I'm given any other function of x and y to obtain the variance, then I will just have to get the variance of x using the formulas we've defined. Expected value of x, variance of x is expected value of x squared minus expected value of x squared. Then I will get the covariance as the expected value of xy minus expected value of x times expected value of y. And finally, I get the variance of y using the same formula as that. After I obtain those variances and covariances, then for any other function of x and y, all I have to do is impute the a and b's. So that if I'm given a function such as 3x plus 4y, then my a is 3, my b is 4. So in this formula, after I obtain the covariance and the variance, all I have to impute is the value of a, which will be 3, and the value of now if I'm asked to obtain that variance, and the value of b, which will be equals to 4. So you have to know that derivation, and you have to be able to apply it. So we can use this first method. Alternatively, we can have it in the format of a matrix. So in matrix form, if I'm given a function, say ax plus by, I can write it in matrix form as A, B is Roman Catholic, Roman XY. So that if I solve this matrix, I'm going to have AX plus BY. So I can put it in matrix form in that format. After I put it in that format, then I'm going to call this is a matrix of constants, call it C prime, which means it's in transpose. It's transposed the way it appears there, which means C is a column matrix AB. And then we can call this matrix of variables, call it maybe Z. This is a matrix now of variables, and this is a matrix of constants. So from there, the variance of AX plus B can now be written if I assume that my variance covariance is given by sigma. Then I just need to multiply C, my C transpose, times sigma times C. But now the sigma is a variance covariance matrix. A variance covariance matrix normally has the variances of the individual. Let me write it on the board, because up in a slide too much, I'm unable to. The variance covariance matrix So the variance covariance matrix it is usually, we denote it as sigma, and it is usually a matrix that has the individual, so variance of x on this column, hii diagonal ilikuwa inaitwa the primary ama the principal diagonal. Then we have covariance of xy and covariance of yx. Covariance of xy and covariance of yx are equal. So these values will be equal. So that if you have more than two variables, then you expect variance of x, variance of y, variance of z. If you're dealing now with 3 variables, and then here you'll have the covariance of, say, xy, and here you'll have the covariance of yx. Here you'll have the covariance of, say, yz, and here you'll have the covariance of zy. Here you'll have the covariance of xz. Here you'll have the covariance of zx. So you're going to notice that these values will always be equal. Covariance, these two covariances will be the same, these two will be the same. And then on this leading diagonal, we are going to have the variances. So a matrix that represents the variances and covariances is what we are calling the variance covariance matrix. So in short, what I'm saying is that using the matrix form, using the matrix format, we are now just going to have to break down our ax plus by. Our ax plus by will be written in the format I've told you, that is ab into xy. And then we are going to have a sigma, that is the variance covariance for 2 variables. So we are going to have variance of x, variance of y, and then we have covariance of xy, and the covariance of yx. So these are values that you can obtain. Given your PDF, we have just seen how we can obtain the covariance and how we can obtain the variances. So this matrix is just a matrix of the variances and covariances. And we are saying to now obtain the variance of any function of x and y. I just need to take this matrix of constants. I've said we call it C, a matrix of constants. And this is a matrix of variables, call it Z. You just need to take C prime, Z, C transpose now. The prime here is for transpose, times C. So I'm going to have my AB. As you can see here, AB. And then that sigma, that sum, this is not a sum. I've told you this is the notation we still use for the variance covariance matrix, capital sigma. Meaning you're dealing, because sigma, small sigma is variance. So capital sigma is the variance covariance matrix. So we have capital sigma AB. So we have AB, that covariance matrix times AB. So all you have to compute, if you just solve this matrix, you're going to have A variance X plus B covariance of XY, and then times the next term will be A Roman Catholic. So you'll have A covariance XY plus B variance Y times AB. You do the same thing again. Here you'll have A variance X plus B covariance XY times A. So that will give you A squared variance X plus, because we are multiplying by A, So this will be AB covariance XY. Same thing, this other second bit, because you take the row values times the column. So this is the row value times this column. You're going to have, again, A, now you're multiplying by B. So you're going to have AB covariance XY, and then B times B variance X will be B squared variance Y, which is the same output that we got using the other approach that we used. And it can be shown that it can be extended to more than 2 variables, like in that second bit there. You see the case when you have more than 2 variables, that is 3 variables. We have X, Y, and Z, and how you can use this variance covariance technique. The matrix approach is usually ideal when dealing with multivariate data. So when we are dealing with data that has more than 2 variables, that is when we use this variance covariance mostly, because it makes the working easier and more direct. So you can see how that was extended. It's still the same thing. You see the variance covariance for 3 variables. We have the variances on the leading diagonal. The covariance is there. So for 3 variables, you will have to get the variance of X, variance of Y, variance of Z, and then the various covariances. Actually, you'll just need the variance of XY, variance of XZ, and variance of YZ. That will be enough. After you get those covariances and the respective variances, the expansion is as shown there. So there is this example here. We are given the variance covariance matrix of X and Y. So this simply means that the variance of X is 3 and the variance of Y here is 2. And then the covariance, as you assume, they are the same. I told you the covariance is the same. The covariance of XY is equal to the covariance of YX. So they are the same, a third. And then you're expected to compute the variance of this function of X and Y here. That function of X and Y, of course, you know, first of all, the variance of this value that has no constant, a variable on it, the variance of -5 is 0. So we can as well ignore that because it has no variable tied to it. The variance of that value will go to 0. So our only interest will be to compute the variance of 3x plus 4y. That, going by definition, should be a squared variance x plus b squared variance y plus 2ab covariance xy. You're given the covariance, you're given the variance, you're given the value of A is 3, the value of B is 4. So if you just input that in the formula that we've just looked at, that is just simple imputation, you should be able to get that the variance of that new function of X and Y is 67. You can copy that down before we proceed to the conditional expectation and variance, unless there are any questions on that. This is just an application bit. I'm going to share another exercise with you after the class is done. But that is the main concept. You just need to know this formula and know that if it is minus, it will only affect the covariance bit. This is what will become negative, minus 2 covariance, 2ab cov xy. But the variance of A, X, and Y is the same. As we ponder on that, when you're dealing with these variances, if X and Y are independent, this is a note. If X and Y are independent, you have to know that the variance, if they are independent, remember we said if X and Y are independent, the covariance is 0. But a covariance of 0 does not imply that X and Y are independent. But if X and Y are independent, the covariance is 0. So the variance of AX plus BY, if X and Y are independent, will simply be A squared I normally teach this here. Then when I go somewhere else and recall it, nobody will ever remember I said anything of this caliber. It will be a squared variance of x plus b squared variance of y. Why? Because the covariance term, the 2ab covariance xy, will go to 0 because the covariance will be equals to 0. So if x and y are independent, this is how you get the variance of any function of x and y. Any question before I proceed to the conditional expectation and variance? Emmanuel, I like the way you just agree to everything. I'm hoping to resume physical if and when hamtaniambia nirudie hizi vitu tena. Tukiresume physical, I'll just pick it from where we'll have left. So we proceed to the conditional expectation. I don't know if you've captured that before I proceed to the conditional expectation. No. Ondara, you have no idea how wide this course is. This course, saizi tuko week 5 ama ndio 6. All I know is that we are supposed to have been done with joint moment generating functions. So the best I can do is get to those joint moment generating functions. If I don't get there, and we're almost halfway through the semester, there will be trouble ahead. And of course, we need a cut. Now, I don't know, since there are some prospects of resuming physically, I'm waiting for the order. We still have a long way to go because we still have the joint moment generating functions. We have the transformation of variable techniques. We have the order statistics. We have the bivariate distribution functions. We have too much to cover, just to say the least. So let me just finish with the conditional. Since we've been dealing with these concepts of bivariate, the conditional is just from the conditional distribution of x and y, how do I get the conditional expectation and the conditional variance? It won't be something heavy for you to digest. It will be something quite direct. And as I promised, it won't take 30 minutes. So just allow me to finish with this conditional, ndio next week tuanze moment generating nione at least there is some progress. Otherwise we'll have set ourselves up for frustration. So Goti, I wish I could stop there. I also wish I could stop there, but time is not on our side. So our cut will be next week. Next week. Mmesikia kuna cut next week? Msijifanye hamkuambiwa. Sijaambia hata class reps, but nitawatumia message. We had said 2 weeks from last week. We said 2 weeks. So cut next week. 1 week has gone. The other week. Kwa hivyo mkireport kesho, ama sijui ni lini mna report, Wednesday mkuwe tayari kufanya cut ya probes 2. Sawa sawa? Aya. Moving on swiftly. Hiyo kati ikipitisha hapo itakuwa mzito sana. So acha tuifanyie hapo. So I want us to introduce the concept of conditional expectation and the conditional variance. Conditional expectation is similar to the conditional distribution that we dealt with, but now here we have the expected value of, say, y given x, or the expected value of x given y. Now here the catch is usually very simple. If you're asked to obtain the expected value of y given x, you first need to get the conditional distribution of y given x. And here we say conditional distribution will be f of xy divided by f1 of the marginal of x, or the marginal of whatever is given. So the first step is you obtain, once you are asked for the expected value of y given x, or in the variance definition, you're asked for the variance of y given x. This is the conditional variance and the conditional expectation. The first thing you do is obtain the conditional distribution of y given x. Kama ni expected value of x given y, first obtain the conditional distribution of x given y. Then from there, it's just as easy as the expected value of y given x is y times the conditional distribution of y given x, dy. The expected value of x given y is x times the conditional distribution of x given y. As simple as that. So you just need to get the conditional, kani expected value of x given y. You need to get f of x given y. Ukishapata hiyo sasa, hii yenye unataka kuget expected value. Remember unataka expected value ya x given y. So the moment you obtain the conditional distribution of x given y, you've already handled this given part. So now you're just left with the expected of x. So this is why we are taking the integral of x times f of x given y. Ukiambiwa get expected value of y given x, to take care of this part you are given, kwanza find the function of y given x. Then now you're only left with the expected value of y. That is why you take the integral of y times f of y given x dy. That is all you have to call when you're getting conditional expectations. So you first get the conditional distribution. From the conditional, you're only left with multiplying it by x or by y, or whatever function of x or y you're given will now come here. After you get this, it will have handled the given part. So you'll only be left with the expected of whatever function of x or y you're given. And of course, if it is discrete, this changes to a sum. If it is discrete, that changes to a sum. The other thing you need to note is that the conditional expectation, say the conditional expectation of x given y, this will always be a function of, it will be a function of y, not f of y. It will be This will be a function of y. The expected value of x given y will always be a function of y. And the expected value of y given x will always be a function of x, of whatever you're given. The conditional expectation of x given y will be a function of y, and the conditional expectation of y given x will always be a function of x. So just take note of that. That is for conditional expectations. For the conditional variance, if you're asked for the variance of y given x, say x is equals to some value x, of course you'll be given. This is the same as taking the expected value of y squared given that x minus now the conditional expectation of y given x, all this squared. So once again, since you can obtain this expected value of y given x by first obtaining the conditional distribution of y given x, and then multiply that by y and integrate it over the interval of y, that will give you this. The same thing as here. The expected value of y squared given x, you will first get the conditional distribution of y given x, and then from there you're going to get the integral of now y squared times f of y given x dy. That will give you this term. So for the variance, you'll just take this value, and since we are dealing with expectations, I've told you every time you're dealing with expectations, your answer should be a constant. It should not be a variable. So you're just going to take this value minus the conditional expectation squared, and that should be able to give you the variance of x given y. I would like us to look at an example that is going to work that out. One discrete, one continuous, and then now we can call it a day. And Ogoti, you can now digest everything at once. So I want us to look at this example. Let x and y be jointly distributed random variables. They each have a PDF of 2 fxy, which is 2. And we looked at this question somewhere else, but I know it wasn't in expectations, so we'll still have to compute those expected values. But I think we obtained the marginal. For this question, we obtained the marginal of x and y, didn't we? We expected to obtain the conditional expectation of x, of y, x given y, and the variance of x given y. So since we are asked for x given y for both, you're going to do, as an exercise, you're going to look at expectation of y given x and variance of y given x. So for now, we will deal with x given y. So the first thing we need to do is compute the conditional distribution of x given y. Can we start there? We want to get f of x given y, so that we can have f of x given y will be equals to f of xy all over f2 of y. So you recall the marginal of y. Obtain the marginal of y really fast, and then we obtain that conditional distribution of x given y. Into the marginal of y itakuwa, you integrate over the interval of x. X ranges from 0 to y. You see it is bound by y here. So x ranges from 0 to y, 2 dx. So you're going to get to x in the interval of 0 to y. So when x is y, you have 2y. When x is 0, you have minus 0. So this is just 2y. The marginal of y is 2y. So if you have 2y and you have 2, then the conditional f of x given y should be equals to 2 over 2y, which will simply be equals to 1 over y. So that is the conditional distribution of x given y. So we have said to now obtain the expected value of x given y, we have to take the integral of x times f of x given y. F of x given y is 1 over y. So you're taking the integral. This is with respect to x dx. So you're taking the integral of x times 1 over y, that is x over y dx. Of course, your x ranges from 0 to y. It hasn't changed. So x over y dx. So this will be x squared over 2y in the interval of 0 to y. So in the interval of 0 to y, if you substitute for when x is y, you have y squared over 2, y squared over 2y. So that is y over 2. When x is 0, that is undefined. So we have our expected value of x given y will simply be y over 2. Kwa pamoja hadi hapo? Are we together? So that now, if we want to get the variance, we just need now to get the expected value of y squared given x squared given y. And that will be x squared f of x given y. So this will be x squared over y. See here, we are just integrating x squared over y dx. You integrate that function, you get the expected value of x squared given y is y squared over 3. Y squared over 3. That is just by integrating x squared over y with respect to x. You get x cubed over 3y. So when x is y, you have y cubed over 3y. So that becomes y squared over 3. When x is 0, again that is undefined. So we are going to have the expected value of x squared given y is y cubed over 3. And then now, since you had already obtained the expected value of x given y is y over 2, you're taking y squared minus y. So we have y squared over 3 minus y over 2 squared. Once you simplify that, you're going to get y squared over 12. And as we said, you notice that variance is a function of y. We said the expected value, we have always said expected values are constants. But for this conditional expectation, I've told you, note, the expected value of x given y is a function of y. The variance of x given y is a function of y. Expected value of y given x is a function of x, and the variance of y given x is a function of x. So whatever is given, the expectation and conditional variance will be functions of whatever is given. So that now here, I'll just have to change. If I'm told y is equals to 2, to get that variance, I just need to input when y is 2 there. If I'm told for y is equals to 5, I just need to input there when y is 5, so that I can get the conditional expectation and variance. Kwa pamoja? copy down this other question really fast. I give you we work through the solution and call it a day. If there are no questions, that's why. This value here is 2 over 8, in case it's not clear. All of them are over 8. So you have 1 over 8, 1 over 8, 2 over 8, 3 over 8. And they should sum up to 8 over 8. So you have 1, 2, 3, 1, 1 over 8. Is it done? You're expected to compute the expected value of y given x and the variance of y given x. Additional information there is for when x is 1 and 2 and when x is 1 and 2 for both instances. So you're getting the expected value of y given x is 1, expected value of y given x is 2. So if we get this expected value of y given x, it will be a function of x. So after we obtain it, we just need to substitute for when x is 1 and when x is 2, and we'll get the constant value, the constant expected value. Same as for the variance. Once we obtain the variance of x, of y given x, it will be a function of x. So we'll just substitute for when x is 1 and when x is 2, and we get the constant value of the variance when x assumes those two values. Let me share the working. You can take it down. So you start by getting the expected value of y given x. The expected value of y given x that expected value of y given x will be equal, as we have said, to the sum of y times f of y given x. So the first thing you need to get is the f of y given x. And now we said when we are dealing with this discrete function, we need to get it as f of y at each level. So we are given at the level when x is equals to 1 and 2. X assumes the value is 1 and 2. So when x is equals to 1, you get the conditional, and then when x is equals to 2. you get that conditional distribution for when x is 1 and when x is 2. And then you're just going to have to multiply. When x is 1, you substitute for the values of y. So you're going to have, when x is 1, you will take your expected value of y given x will be equals to, you're going to have 0 times f of 0 given 1 plus 1 times f of 1 given 1 plus x imefika 2 times 2 times f of 2 given 1. So when you compute these values from your table, f of 0 given 1 will be f of 0, 1. It will be the f of 0, 1 all over f of when x, the marginal of x when x is equals to 1. F of 1, 1, 1 given 1 will be f of 1, 1. That is the joint distribution when x is 1 and y is 1, which is 1 over 8, divided by the marginal when x is equals to 1. The same as this, you're going to have the joint of 2, 1. That is when x is 2 and y is 1, divided by the marginal of x is equals to 1. And then after you obtain those values, you're going to, this is when x is 2 and y is 1. Sorry, this is given x. So this is for x10, f10, not 11, 01, f10, f11, and f12, which is as shown, here. So you obtain that conditional expectation when x is 1. Same thing when x is 2. Again, now you substitute for when x is 2. So you'll get f of 0 given 2, x of 1 given 2. That is now y given x. So when x is 0, you have x of 0 given 1. This times 0 is because you're taking y times f of y given x to get the expected value. So again, y is 1 times f of y is 1 given x is 2. And then when y is 2, you have 2 times f of y is 2 given x is 2. So you use the formulas that we use to obtain those conditionals, dividing by the marginals. You have the joint divide by the marginals, and you're going to end up with the expected value for y when x is 2, and the first one will give you the expected value for y when x is 1. Then you do the same thing for the variance. For the variance, you're now going to be expected to get expected value of y squared. That is what you won't have for the variance, because you're taking expected value of y squared given x minus expected value of y given x, all this squared. So in this first question, you've obtained expected value of y given x is 1 and expected value of y given x is 2. So now here you just need to get expected value of y squared given x is 1 and expected value of y squared given x is 2. Same formula, but now instead of multiplying by y, you're multiplying by y squared. So you'll have 0 squared, 1 squared, and 2 squared, multiplied by the same functions you used in the first evaluation. So that will yield again the expected value of y squared given x is 1 and x is 2. Then from there you can compute the variance using the formula for conditional variance. And I believe once you go through that, you'll have mastered and digested and understood the concept of conditional expectations and variances. Any other question? Any question regarding what we've learned today? You can take down that question at the bottom as an exercise and compute the expected value of x given y is equals to 1 and the variance of x given y is equals to 1. So this one, instead of dealing with all the y values 0, 1, I just need for 1 when y is 1. I am done. From there, we should be able to move to the joint moment generating function next week. I told you it won't take 30 minutes. So is the concept understood? Is there any question that I need to answer to?
You have called is not